Alright guys, welcome to part 2 of the VSEPR video. I'm going to try to go through these ones a little bit faster, but feel free to pause the video at any time if you, and go back and all those things. But I am going to move a bit quicker through the rest of this. So our next Lewis diagram is for methane, CH4, so it looks like that. And then if I look at the electron pairs around that central carbon, there are just 4 bonding pairs. Okay, and we already talked about how if you have 4 electron domains, that gives you a tetrahedral basis shape. So that's like that. Okay, and then a 3D diagram. You put your central carbon atom and then that same tetrahedral strategy I used before. So I've got 2 bonds in the plane of the page, 1 coming out. I use a wedge to show that. And then 1 going back in, and I use dashes to show that. And then there's hydrogens on the end of all of those. Okay, because all of these electron domains are bonding pairs, the molecular geometry is the same as the basis shape. So this is a tetrahedral molecule. Okay, and then we already mentioned earlier that in a tetrahedral molecule, the bond angles are 109.5 degrees. Okay, moving on to ammonia, looks kind of similar except we've got a lone pair here, so 3 bonding pairs, only 1 lone pair, so it's still a tetrahedral basis shape, and you'll notice the next few we do are all going to be tetrahedral. Okay, so then I've got ammonia in the middle, nitrogen in the middle, and then I'm going to have 1 hydrogen in the page, 1 coming out of the page, and 1 going into the page like that. And then my lone pair on top. I don't need to fill in those lone pair electrons. Looks like that. Okay, so in this case, I do have 1 lone pair, so my molecular geometry isn't going to have the same name as a tetrahedral geometry. It's going to be called, just like our first example was, trigonal pyramidal is how we say this word. Okay, and because of that lone pair on top pushing those non-bonding or those bonding pairs down a little bit more, that extra repulsion, I have a bond angle slightly less, 107 rather than 109.5. Just to give you some context for this, so this is that tetrahedral molecule that I had built before. And trigonal pyramidal molecule, you just basically take one of these guys off. That's what the shape would look like, kind of like that. You can see it on the side too. Okay, so not trigonal planar because there is an angle less than 180 degrees right here. All right, next one, water. So hopefully your Lewis structure looks like that. Now the Lewis structure, you might have drawn it in a bit of a bent shape or whatever. It doesn't really matter what the shape of the Lewis structure is, as long as you've got a good 3D diagram over here. Okay, so I've got 2 bonding pairs here, 2 lone pairs. So that's still a total of 4 electron domains, so a tetrahedral basis shape. Okay, but only 2 of these are actual bonding pairs. So when I draw my H2O molecule, I'm actually going to kind of rotate it a little bit just for the sake of the way the picture looks, something like that. Okay, and this is called a bent geometry, or sometimes you'll see it called V-shaped. Okay, and just for a little bit of context there, so this was the one I was just showing you for ammonia. If I take 1 more bonding pair off, then I get something that looks like a water molecule, like so. Okay, and the angles get even smaller because of the 2 lone pairs repelling, so this is about 105 degrees. All right. So now we're going to move on to an example with an expanded octet, phosphorus pentachloride. So in this case, I have 5 bonding pairs. Okay. When you have 5 electron domains around the central atom, the basis shape is called trigonal bipyramidal. Okay. And what that looks like is this right here. Okay, now it looks a little wild. The way that I like to think of it is we've got these 2 these two right here in what I sometimes call the axial position. And the bond angle there is 180 degrees. And then if I rotate it, you see that you have 3 in these trigonal planar positions. So this bond angle right here is 120 degrees. Okay, so we've actually got 2 different bond angles that we look at here. We look at the 90, if I'm looking from that perspective, and then I look at the 120 if I'm looking from that perspective. Okay, trigonal bipyramidal, because it's like if you put it like that, it's like a trigonal pyramid with 2 guys coming off the top, and then I can rotate it, and there's like a second pyramid there. I think that's why it's called trigonal bipyramidal. When I draw that, though, put my central phosphorus, and then I'm going to show 3 bonds in the plane of the page. Okay, and these angles are supposed to be about 90 degrees, so Cl, Cl, Cl. And then I've got 1 chlorine coming out of the page. I'm going to stop filling my wedges in just because it's not really necessary. And 1 going back into the page. So that would sort of be, hopefully I can match this up, so that would be kind of that perspective of the molecule. So you've got these 2 chlorines, and then this one, these are all on the plane of the page, and then you've got this one coming out of the page, this one going in. Okay? Now, all of my electron domains are bonding pairs, so this name is also trigonal bipyramidal. And I want to list both my possible bond angles. I've got the 90s and the 120s. Okay, these ones are 90, these ones be 120. All right, next one, sulfur tetrafluoride. So here, my Lewis structure looks like this. So I've got 4 bonding pairs, and I've got 1 lone pair. So once again, I'm dealing with 5 total electron domains. So it's trigonal bipyramidal. Okay, so that looks like that. Now, in this one, I'm going to put in a lone pair. And you can look up online sort of the logic behind this. So you kind of have the option of putting a lone pair in either this position, so leaving something that looks like that behind, or one of the equatorial ones, something that looks like that. And it turns out that this is actually the shape that we see. And that's what we're going to describe and draw here. So the way we normally draw that is I'm going to show my 2 chlorines in the plane of the page, and then I'm going to kind of show it, oh, sorry, I'm using the wrong elements looking at the example up above. So sulfur, fluorine, fluorine, and then I'm going to show 1 fluorine coming out of the page, 1 going in, like that. And we call this a seesaw. Okay, and we call it a seesaw because if I put it like this, then it acts kind of like a seesaw or a teeter-totter. Okay. The bond angles there, so if I look at this bond angle, we've got a 180 there. If I look at this bond angle, that's a 90. And then if I look at this bond angle, 120. Okay. There is obviously a little bit of extra repulsion from the lone pair that's in this position, but from my experience, IB doesn't seem to ask so much about the bond angles in a shape like this. And they focus a lot more on things that come from a tetrahedral basis shape. Okay, so I'm just going to list these as the numbers that I would just see in the normal basis shape. Okay, although if you wanted to get really technical, these angles would all be a little bit smaller from that extra repulsion. So you could even say less than. Okay, if you want it to be very clear. All right, that was pretty quick. So let's do this last page right here. Let's see if we can get through these even quicker. So we've got chlorine trifluoride. Lewis diagram looks like that, meaning that I have 3 bonding pairs, 2 lone pairs. Basis shape is still, because I have a total of 5, trigonal bipyramidal. Okay, 3D diagram, I've got chlorine. The easiest way to draw this is actually called a T shape. So I'm going to keep my 2 axial position fluorines, and then I'm going to have 1 more fluorine in the plane of the page. And there are these 2 additional lone pairs that are sort of repelling, but ultimately my molecule is just a T shape. Okay, so I've taken a complex geometry and it looks a lot more simple here. And then my angles are 180 if I'm looking at this bond angle, or 90 if I'm looking there. Okay, and just to give a little bit of context, so that would be like if I took 1 more pair off here and I end up with a T shape like that. Okay, so you can see the angles are all kind of right angles or straight lines. All right, and then last one where I have 2 bonding pairs and 3 lone pairs, still trigonal bipyramidal. But in this case, 3 of my spots are taken up with lone pairs, and that ends up being all 3 of those equatorial positions. And then left, even though there are 5 electron domains, I'm left with a very simple geometry, just 1 straight line. Easy. Okay, then I have 3 more shapes, and these ones are all going to be based around what's called an octahedral geometry, so where you have 6 electron domains. So I'm just going to take a quick shortcut and fill that in for this box right here. So these ones are all going to be octahedral. Now in this one, obviously, I've got just 6 bonding pairs. The way I would draw the 3D diagram for this, I've got sulfur, I've got my fluorines like this, and then I've got 2 fluorines coming out of the page like this, and then 2 more fluorines going back into the page like that. Because all of these are bonding pairs, I can just use the same name. This is octahedral. And octahedral molecules are perfectly symmetrical. Every bond angle is 90 degrees. Okay, so just once again, this is an octahedral molecule. Okay, everything's a 90-degree angle. All right. CLF5. So I'm actually going to pause the video and fill in some gaps here before continuing. So just give me 1 second. All right, so here I filled in my final 2 rows. So for CLF5, chlorine pentafluoride, I've got 5 bonding pairs, 1 lone pair, still an octahedral basis shape because those total up to 6 electron domains. The way those organize, it's just I look at my octahedron and I take 1 piece off. So you end up with this shape right here. Okay, so just with the bottom of the octahedron missing. And that is called a square-based pyramid, or just a square pyramid. Like that. Okay. And then our final one, xenon tetrafluoride. I don't really want to get into how xenon could possibly make a bond, given that it's a noble gas, but let's just accept that this is a molecule that you can create in really high pressure situations. So once again, 4 bonding pairs, 2 lone pairs on this one, total of 6 tells me it's an octahedral basis shape, but I'm taking 2 of my lone pairs away. So actually, rather than taking away like this one and ending up with kind of another version of a seesaw, I take away this one right here, and I end up with just what we call a square planar molecule. Okay, so this one right here is square planar. Okay, and sometimes you see square planar molecules drawn kind of like this, sort of with that taken off of the chlorine, but yeah, I think it's easier to just draw all the bonds in the plane of the page like that, square planar, and then those would be your bond angles. Okay, thank you for watching.